Okay guys, we are looking at partial derivative. So I'm just going to go over partial derivatives, the basics, and I'm going to do the questions and stuff like that. So okay, with partial derivatives, we apply partial derivatives when you are looking at a multivariable function. So if you have your function z is equals to f of x y, so z is with respect to x and y. So if you're finding the derivative of this multivariable function, you have to find the derivative with respect to x and the derivative with respect to y. So with this one, unlike when you're looking at a normal function like y is equals to f of x, so dy dx is the same thing as f dash of y. So this is for when y is when y is a dependent variable and x is an independent variable. But here we have two independent variable, which is x and y, and our function is c. So how do you find the first derivative of this one? The first thing, you find the first derivative with respect to x, and then you can also find the first derivative of z with respect to y. So this is how we represent derivative using partial. This is partial derivative. This is how you represent derivative when you're looking at multivariable function. So there's something that you have to note here, especially with the notation. So if still we have z is equals to f of x y, the notation is very important. If you're differentiating this with respect to x, it's going to be d dx, which is the same thing as z x subscript x. This is very important, and in this case y is going to be a constant. When you're differentiating z with respect to x, y is going to be a constant. You treat it as a constant. And again, when you're differentiating z with respect to y, we are going to have z y, which means here x is a constant, right? So those are the major things that you have to note when you're looking at partial derivative, especially the notation. So with our syllabus, we're going to look at first derivative and first derivative and second derivative, especially with this one, with the partial derivatives. And with the partial derivatives, we still use the same rules that we used when we're looking at the normal derivative, whereby we're going to use the chain rule. It still applies. Product rule, it still applies, and also the quotient rule, it still applies. So all of these rules still apply. So our main focus is to apply these ones when you're solving questions. Okay, so now and don't mix up. This is a Kelly D. You are using Kelly D when you're using partial derivative. This is the Kelly D. We are using Kelly D. So okay, now I want us to look at the notation, especially for the second derivative. Remember we have remember you have z is equals to f of x y, right? So we are saying you can differentiate this. You have dz dx and you have dz dy, right? So now with dz, we want to find, we differentiated, remember we differentiated with respect to x, with respect to y. And when we are finding, this is the first derivative, when you are finding the second derivative, we are going to do the same thing again. We are going to differentiate this with respect to x, with respect to y, and the same thing here with x with respect to y. So let's start with this one. So d dx of dz dx, sorry, and then we're differentiating again dy of dz dx. So what did I just do? We had dz dx, isn't it? I differentiated it with respect to x, and he decided I differentiated this with respect to I differentiated this with respect to y, isn't it? The same thing that I'm going to do this side. I'm going to differentiate my function this with respect to x, so I'm going to have dx of dz dy, and then I'm going to differentiate this with respect to y, dy of dz dy. And then now let's simplify this. If you simplify this, obviously it's going to be d2z dx squared, which is the same thing. This is the same thing as z x, and then this is going to be d squared z dy dz. And here you have to be careful. This is going to be z. Remember, we're differentiating z with respect to x, right? We're differentiating z with respect to x by dy, which means this is going to be y. Same thing here. We are differentiating dz dy with respect to what? With respect to x. So we are differentiating zy with respect to what? With respect to x. So even here, this is going to be d squared z over dy squared. Here we are differentiating zy with respect to y, right? So this is how it's going to be. So now you have dz dx squared is equals to zx x. You have d squared z over dy d over dy dz. This is equals to zxy. You also have this one. When you simplify this one, you're going to get d squared z over dx dy, which is equals to zyx. And lastly, you have d squared z over dy squared, which is equals to zyy. So this is very important. So if you are looking at this, with the first derivative, we have 1, 2, right? With the second derivative, we have 1, 2, 3, 4, which means if we are looking at the third derivative, we're going to have 8. Then the fourth derivative 16, but then we are restricted only with the second derivative. So you have to understand the notation. And then now we are going to do questions, just simple questions where you are solving an ordinary multiple variable function that we can use. So let's say you have z is equals to 4x cubed y plus 4xy squared. So we have this multivariable function. This is obviously z is equals to f of x, y, isn't it? So now here you want to find the first derivative. You want to find the first derivative and the second derivative of this one. So the first derivative, we are differentiating with respect to x and y, obviously. So let's differentiate with respect to x first. So dz dx is going to be what? Remember, if we're differentiating with respect to x, we are saying y is going to be what? Y is going to be a constant. So here we treat y as a constant. So coming to this first term, differentiate this with respect to x. Obviously, it's going to be 4 times 3x minus 1 is 2, right? Times, this is a constant. So 4y is a constant. This is just y. Plus, by differentiating this with respect to x, is going to be what? 4y squared. So this is going to be 12 12y x squared plus 4y squared. We differentiated this with respect to x, so this is what you get. And we know that this is also what? This is also zx, right? And then again, let's differentiate the same function with respect to y. So dz dy is going to be what? Now x is a constant, which means when you differentiate the first term, it's going to be 4x cubed, and then differentiating the second term is going to be plus. We are differentiating with respect to y, which means x is a constant, so we're going to have 4 times 2, right? 4, because this 2 is going to multiply the 4 times 2 xy, because it's going to be minus 1 here, so xy. So this is going to be 4x cubed plus 8xy. So this is the same thing as zy, right? So now we have our first derivative. We have dz dx, which is equals to zx, which is equals to 12y x squared plus 4y squared. And this side we have differentiated z with respect to y, which is equals to zy, which is equals to 4x cubed plus 8xy. So now we need to find the second derivative of this, right? We need to find the second derivative of this. And also when you're finding the second derivative of this, we know that we need to have 4, right? Because we need to find zxx, zyy, zxy, and also zyx. So okay, so now starting with this one, differentiating this one again with respect to x and y. So let me differentiate dx of dz dx. So I'm differentiating this again with respect to x. So this is the same as what? This is the same as d squared z over dx squared, right? Which is also equals to what? Zxx, which is equals to what? So I'm differentiating this with respect to x, which means y here is going to be a constant. So if y is going to be a constant, what am I going to have? I'm going to have, from this, I'm going to have 2 times 12, which is 24, 24yx, because then the x value is going to reduce by 1, right? So I have 24xy. And then with 4y squared is, since we're differentiating with respect to x, 4y squared is all a constant, right? Which means it's going to be 0. When I differentiate this with respect to x, it's going to be 0. So zxx is just 24y, it's just 24yx. And then now I'm going to differentiate the same first derivative with respect to y now. So y of dz over dx is equals to d squared z over dy dx, which is equals to what? Remember, I'm differentiating zx, right? This is zx. Now I'm differentiating with respect to y. So this is going to be zxy. And then this is equals to what? Then coming back here, we are differentiating now with respect to y, which means x is a constant, which means we're going to have the first term, we're going to have what? The first term we are going to have, if we're differentiating with respect to y, we're going to have 12 x squared, right? Because we're differentiating y, x is a constant, plus the second term we're differentiating with respect to y is going to be 8y, right? Because 4 times 2, then you minus 1. So this is what xy is. So I've differentiated this one with respect to x and y. Now I come again with the first derivative. I come up back to zy, right? I need to differentiate zy again with respect to x and y. So we have we have, let me just draw a line. We have zy. Okay, let me mark this one. And then 2. We need 2 more, which is z. We have zy, right? Which is equals to 4x cubed plus 8xy, right? Which is the same thing as this. So now I need to differentiate this with respect to y in respect to x. So obviously we know that zy is dz dy, right? So now let me first differentiate it with respect to x. So d dx of dz dy is the same thing as d squared z over dx dy, which is the same thing as what? We are differentiating zy with respect to x, right? Which is equals to, so let's differentiate this one with respect to x. If we are differentiating this one with respect to x, y is going to be a constant. So we are going to have what? We are going to have 4 times 3, which is 12x, right? And then we are going to have, for the second term, we are differentiating with respect to x, y is a constant, so we're going to have plus 8y, right? I hope you guys are seeing this. And now we have z, yx, which is equals to 12x, or this is x squared because this was x to the power 3. So 4 times 3 is 12, and then you minus 1 here is 2. So this is zyx, and then now I need to find what? I need to find the now we're differentiating with respect to y, differentiating dz dy again, which is equals to d squared z over dy squared, isn't it? And then this is the same thing as we're differentiating y with respect to y, which is equals to what? Now x is a constant here. If x is a constant, we're differentiating in terms of y, this part is going to be 0. And then we're going to differentiate this part, we're going to get 8x, right? So now, what is our task? So now we have differentiated everything, right? We've differentiated everything. So we have zx, which is the first derivative with respect to x was 12x squared y plus 4y squared, right? It's here, zx, this was cx, and then now we have zy is what? This is zy is 4 x cubed plus 8xy, and then we differentiated this to z to get z x, which was 24xy, right? And then also differentiated z x y, these are the second derivative, which was 12x squared plus 8y, and this side we found z yy to be what? Zyy to be 8x, right? Zyy was 8x, as we see here, and then also zyx was what? Was 12x squared plus 8y. So this is what, these are our working for the function, for this function. Z was equals to 4x squared y plus 4xy squared. So this is how we go about solving this one. Okay, and then now I want us to look at sort of like a problem that you might find in the exam, an exam-based problem. So if you have a problem whereby we are given that z is equals to x squared sine, we're given that z is equals to x squared sine x minus 2y, and then you're asked to find a, you're asked to find d squared z over dx squared, and b, you are asked to find d squared z or dy squared, right? And then they are saying show that d squared z over dx dy is equals to d squared z over dy dz, which is actually equals to 2x squared sine x minus 2y minus 4x cos x minus 2y. So these are the three tasks that we're supposed to do. So what I want you to note here, guys, this is the same as zyx is equals to zxy, right? I'm sorry, this is x, not z. This is x, not z, right? So they are saying prove that this is equals to 2x squared sine x minus 2y minus 4x cos x minus 2y. So the notation is very important. Okay, so now what is our task? Our first task to find this and this, right? So we're given this is our function. So we have, so this is how we go about doing this one. So we are given that z is equals to x squared sine x minus 2y. So now dz dx is equals to what? dz dx is equals to zx, right? Which is equals to what? We are using, of course, this is u v, right? You're going to use the product rule. So here you are going to have 2x, right? 2x sine x minus 2y plus x squared, and then when you differentiate sine, we are going to have cos x minus 2y, and differentiate what is inside the function sine with respect to x. We are going to have what? 1, because minus 2y is what? It's a constant. So this simplifies to what? This simplifies to just 2x sine x minus 2y plus x squared cos x minus 2y. So we have found zx, we found the z dx. Now we have to differentiate these with respect to x again so that we can find zxx and also find what we are looking for, which is this. So now this is going to be d dx of dz dx, which is equals to d squared z over dx squared, which is equals to z xx, which is equals to what? And then now we want to differentiate this again, right? We want to differentiate this again. We are going to get, we are differentiating this with respect to x. So let's start with this one. Let's differentiate this one with respect to x. We are going to get what? We are going to get 2 sine x minus 2y. That's very important. 2x minus 2y. I'm differentiating this first part plus 2x, right? Then to find the first derivative of sine is going to be cos x minus 2y, and then differentiate what is within sine with respect to x is going to be what? It's going to be 1. So I've differentiated this part. So now I have to differentiate this part, which is plus, with respect to x again, we're going to have 2x cos x minus 2y plus x squared. when you're differentiating cos, you're going to have -1 sine x minus 2y, and then when you're differentiating what is inside with respect to x, you're going to have what? 1, because it's x minus 2y. We know that 2y is a constant, so we just differentiate x to 1 and then the constant to 0. So now this is what we have for d squared z over dx squared. We are going to have what? Let me just write it in a simplified form, and then you're going to collect the terms. So we're going to have 2 sine x minus 2y plus 2x cos x minus 2y, and then plus 2x cos x minus 2y, and then the last one is minus this one. It's going to be minus x squared sine x minus 2y. Okay, I was running out of space there. So now if you could just collect like terms here, we are going to have what? We are going to have this is equals to, okay, this and this you add, you are going to get 4x cos x minus 2y, and then sine x minus 2y, sine x minus 2y. This is going to be plus, obviously you have 2 here, you have minus x squared, so you have 2 minus x squared, then sine x minus 2y. I just factored out sine x minus 2y from both of this term, and I was left with 2 minus x squared. So now we have found what? We have found our first task, which is this. Now we have to find this. So let's differentiate the same function again with respect to y twice. So that's what we're going to do. So let's differentiate the same function with respect to y twice. So this is what we have. We have dz dy is going to be what? So this is our function we're respecting in with respect to y, which means x is a constant. This x squared is going to be a constant. So this one is very easy. We are going to have x squared cos x minus 2y, and then if we're differentiating what is inside here with respect to y, x is a constant, so we're differentiating minus 2y. We are going to get what? Minus 2. So this is the first derivative with respect to y, and then if we simplify this, we are going to get what? We are going to get minus 2 x squared cos x minus 2y. Perfect. So we know that this is what? This is the same as zy. Right. So now let's differentiate this again with respect to y. So dy of dz over dy is the same thing as what? As d squared z over dy squared, which is equals to, which means now we are differentiating this with respect to y again, which is the same thing. This part is going to be a constant because x is a constant. So we are going to have minus 2x minus 2. Okay, this is not squared because we differ. Oh yes, it's squared. I'm so sorry. Let me erase here. This is going to be squared. Yes, this is squared. So now we are differentiating this again. We have minus 2x squared, which is our constant, which is this, and then we're differentiating cos x minus 2y. When you're differentiating cos x minus 2y, we know when you differentiate cos, it's going to be negative 1 sine x minus 2y, and then we differentiate what is inside. X is a constant, so we are going to have 2, right? So if you simplify this, we are going to get what? We are going to get minus, it's what? it's positive, then this minus, we're going to get minus 4x squared sine x minus 2y. So this is what you get. So this is the same thing as c y y. So now we have d squared c over dy squared is equals to minus 4x squared sine x minus 2y. Okay, so now we have found, we have done these two tasks, A and B. Now we need to show that this is equals to this. We need to show that zyx is equals to zxy. So how do you do that? Let's find yx first. So we are going to take dz dy and differentiate it with respect to x. So where did we dz? We're going to take this and differentiate it with respect to x. So we are going to differentiate dx, differentiate dz dy with respect to x. We are going to get d squared z over dx dy, which is equals to what? So this was this function. This was this function. So now we are differentiating this with respect to x. So we are going to have minus 4x, right? We're going to have minus 4x cos x minus 2, or cos x minus 2y. Cos x minus 2y plus, since we're using the chain rule, there's x here, there's x here, using the chain rule, plus minus 2x squared, which means if you're saying plus minus 2x squared, this is just going to be minus 2x squared. Now we are differentiating cos with respect to x. So this is going to be when you're differentiating cos, is minus sine x minus 2y, and then we're differentiating with respect to x, differentiating it everything inside with respect to x. We're going to have what? We're going to have 1 here. So this is equals to minus 4x cos x minus 2y, right? And then minus here is going to be plus 2x squared sine x minus 2y. So this is what we have. And then from here, now we have d squared z dy dx dy. So now we need to find what? We need to find d squared z dy dx, right? Which means we need to differentiate this with respect to y, right? So we want to differentiate dz over dx with respect to y. So this is going to be d squared z over dy dz, and this is going to be what? So we're differentiating all of these. We're differentiating all of this with respect to y, which means x is a constant. That's perfect, because these are going to be constants. So starting with the first one, if we're differentiating the first one, we are going to have x is a constant. We're going to have 2x, which is our constant, right? We're going to have 2x, which is our constant, and then we are going to have 2x, which is our constant. I'm sorry. Give me a second. Okay, we're going to have 2x, which is our constant, and then differentiating sign, we are going to have with respect to y. Differentiating sign with respect to y is going to be cos x minus 2y, and then differentiating everything that is inside, we're going to have minus 2, right? Because we're differentiating with respect to y, plus we're differentiating this second part, so it's going to be what? It's going to be, we have x squared, right? And we're differentiating cos, we're going to get -1, then sine x minus 2y, then differentiate what is inside, cos here with respect to y is going to be minus 2, right? So this is equals to this is minus 2 times 4, or minus 2 times 2 is equals to minus 4x cos x minus 2y, right? And then this times this, it's positive 2x squared plus 2x squared sine x minus 2y, right? So this is what we have. So now you can see that we found this, right? And obviously these are the same. We just proven that these are the same, right? Which means therefore zyx is equals to zxy. We've just proven this. So this is a typical exam question. But it's just a basic one. You just need to know how to apply the chain rule, especially the product rule and the chain rule, yes, especially when you're dealing with trigonometric functions. So now we are going to move to a different concept, whereby now we are applying the principle of partial derivative. I want to talk about what we call total derivatives. With total derivatives, we have, this is how we represent it. So we have du is equals to du dx times dx plus du dy times dy plus du dz. It can continue. So with this one, with the total derivative, this is the typical formula that we use. So then how can we apply this? How can you apply these concepts? So let me just give you an example. If you're given that z is equals to x minus y over x plus y, and then they're saying you are tasked to find dz. So remember, this is no longer curly brackets. This is just dx, this is dx, this is dy, this is dz. They are no longer curly d's, right? So how do you find? Now we are tasked to find dx, right? So how do you do this one? In order for you to find dx, which means for this one, how do you find dz? In order for you to find dz here, you know that you use the same concepts, which means dz is going to be equals to what? Dz is going to be equals to dz over dx plus dz over dy. I'm just using this, and since z is there is with respect to x and y only, so we are going to end with dy. But if z was in respect to x, y, z, we're going to end at z. So now this, we just need to find this. So which means we need to find these two terms in order for us to find dx, and we know how to find dz dx, and we know how to find dz dy. This is a simple concept. So now we have to differentiate this. We have to differentiate our multivariable function with respect to x and y. So let's find dz dx. This is going to be what? Dz dx. Differentiating this, whether you're using the product rule or the chain rule, stay the same thing. So we are going to use the chain rule. We're going to have x plus y, right? And then differentiating the numerator with respect to x, we're going to have 1 minus x minus y. Differentiating the denominator with respect to x, we're going to have 1 again, all over the denominator squared, right? All over the denominator squared. So this is equals to what? This is equals to, when you simplify, you are going to have x plus y minus x, going to minus x here, minus x, then minus is plus, so plus y all over x plus y squared. So this is what we have. So this is what we have here. This is our first derivative. So obviously we need to simplify dz dx. We need to simplify the numerator. If we simplify the numerator, what do we get? We get x minus x is 0, y plus y is 2y. We get 2y over x plus y squared. So this is the function that we get. So that is our dz dx. And then we are going to have to get dz dy now. So dz dy is equals to what? Differentiate this again with respect to y. Still going to use the chain rule. You can use the product rule either way. When you're using the chain rule, you're going to have x plus y. Going to have x plus y. Then differentiate the numerator with respect to y. We are going to have minus 1, and then minus we have the denominator, and then differentiate the numerator or the denominator with respect to y. We're going to have 1 here all over x plus y squared. This is equals to, when you simplify this, we are going to get minus x, we are going to get minus y, we are going to get minus x, we are going to get plus y, right? All over x plus y squared. So this simplifies to what? This simplifies to minus 2x all over x plus y squared, right? So now you've differentiated this with respect to x and y. So you just substitute here to find what? To find dz. So your total derivative here is going to be dz is equals to dx dy. We know that dx dy is what? It's equals to dz dy. It's equals to dz dx, it's equals to dz dx. We know that dz dx is what? This is dz dx. So dz dx, we found it to be 2y x plus y squared, isn't it? Dx, which is this, right? Plus dz dy. We have found dz dy to be this, we have found it to be minus 2x x plus y squared, right? And then what's dy? So this is how you represent your total derivative. This is your total derivative of function z. It's just a basic concept, and this is the formula that we use. So okay, moving to another concept. Obviously, like we can also represent this with the notation that we used earlier, depending on the book that you're using, whereby dz can be dz. Okay, I'm sorry, what happened? Oops. Okay, I'm sorry. Okay, let me continue. So I was saying dz can be what? Dz can be the same as z x dx plus zy dy, if you choose to use this notation. So this is the same as the total derivative. Okay, so now let's move to another concept, whereby now we have to apply still the application of derivative, but we're using the concept of small changes. So we're using the concept of small changes. We're applying derivatives. We're using the concept of small changes. So remember that we said when you're doing calculus 1, dy dx is equals to the limit as delta x tends to 0 of delta, let me write this properly, of delta y over delta x, right? That's what we said. But we said, but if delta x is very small, we're going to have dy dx is approximately what? It's approximately dy dx delta y delta x, So, and then this can be written as dy is equals to delta y over delta x dx. I just remove this ds, multiply it to the other side. So this is the concept of small changes that you are going to use. It's very important, especially in application optimization. It's very important. So okay, let me just expand this concept. If I'm given a function z is equals to f of x1, x2, x3 going to xn, right? Then which means dz, I'm writing the general form of this one. dz is going to be equals to what? dz is going to be equals to dz over dx1 plus dz over dx2 and dx2 plus dz over dx3 plus, obviously goes to the end derivative, which is dz dxn, right? So now, and then this, we can expand this same equation when we are looking at the rate of change, the rate of change for small changes though. So now we are introducing time. So if you are looking at the rate of small changes, which means this is going to be dz dt, which means we're multiplying all of this side with t, right? So this is going to be dz dx1 times dx1 over dt plus dz over dx2 times dx2 over dt plus dz over dx3 times dx3 over dt plus, obviously, goes to dz dxn times dxn over dt. So this is how you can, this is the general formula of using the rate of small changes. This is what you use. So I think this would be best if explained using a concept. Let's solve a problem. So let's say we are given a problem. They are saying the radius of a cylinder, is increasing at a rate of 0.2 centimeters per second, while the height h is increasing at 0.5 centimeter per second. So we are given that we are saying A, determine the rate of change for its volume, for the cylinder's volume, when R is equals to 8 centimeters and H is equals to 12 centimeters. Okay, so we're given a problem here. They are saying the radius of a cylinder is increasing at a rate of 2. It's increasing, which means it's changing at a rate of 0.2 centimeters per second, while the height is increasing, also changing at a rate of 0.5 centimeters per second. So we know a cylinder, right? This is H and then this is R. So they are both changing. So how do you come about solving this one? First of all, you need to know what is the volume, the formula for the volume of a cylinder. So a volume of a cylinder is what? It's V is equals to pi R squared H. If you forgot this one, the volume is equals to the cross-sectional area times the height. The cross-sectional area of a cylinder is a circle. That's why this is the formula of a circle, an equation of the area of a circle, sorry. And then this one is also V with respect to R and H, which is a multiple variable function. Both R and H are changing, isn't it? So that's why we are going to apply this principle, the rate of small changes. So how do you apply this one? They are saying we should determine the rate of change of its volume. So we want to find dV, which means dV here is going to be equals to what? dV is going to be equals to del V del R dr, right, plus del V del H dH. Then since we want to find what, we are finding the rate, so this is dt, this is going to be dt, this is going to be dt. So we are still using the concept of the rate of small changes. So what do we have to do? We need to find d del V del R and also del V del H, isn't it? So del V del R is what? Del V del R is going to be, so differentiating the volume with respect to R, we're going to have 2 pi R h, right? And then we substitute. This is okay. Let me just work it out. Okay. Then now let's differentiate v with respect to h. Differentiate the same function with respect to h. Now it's going to be pi r squared, isn't it? And then now we found del v del r, we found del v del h. And then now, what is dr dt? What is dr dt? Dr dt, we are given that the radius of the cylinder was increasing at a rate of what? 0.2 centimeter per second. This is 0.2 centimeter per second, right? And then also dh dt, the rate at which the height was increasing we were given to be 0.5 centimeter per second. So let's substitute everything here. And we know the value of r. R, they said, is equals to what? R is equals to 8, and also h is equals to 12. We want to find the change in volume, the rate of change in volume of the cylinder when r is equals to 8 and h is equals to 12 at that instant. So dv dt is going to be what? Del v del r is what? We found that del v del r was this, which is 2 pi. What is r? R is 8. What is h? H is 12, right? And then times dr dt. Dr dt is what? It's 0.2 plus del v del h is what? It's pi r squared. We know that r is 8 squared times dh dt. Dh dt is 0.5. So this is the rate of change of the volume. So now estimate, or you just punch this in the calculator, you get your value for the rate of change. So which means you're just going to work this out to find the rate of change of the volume. So this is the common application for partial derivative. This is a common application, especially for the rate of change. When they ask you about geometry, you need to know geometric figures, you need to know the volume, the surface areas, you need to know how to find the areas of different geometric shapes. So if you punch this into the calculator, we are going to have 2 pi times 8 times 12 times 0.2 plus pi times 8 squared times 0.5. Getting something like, getting a dv over dt is equals to 352 over 5 pi centimeter cube per second. This is the volume, or you can write it in decimal, which is 221 point. Since these were given in one decimal place, we can also give this in one decimal place, cubic centimeter per second. 221.2 cubic centimeters per second. So this is how you find the rate of change of the volume. So that's how we are going to be solving these typical problems using the rate of change, the rate of small changes. So now another application, another concept that requires the knowledge of partial derivative, which is the last one. It's okay. Before we move to that one, I want us to look at other typical questions that you might find in relation to partial derivatives. The most common one is when we are given you're given variable u in v, so okay, so it's there. We have what you call Jacobian function. Let's look at Jacobian's function. So what is Jacobian's function? So normally you are given functions with respect to u and v, and then you need to find you have to find dy dx, but you are given two functions with respect to u and v. So how do you come to solve this one? It's actually easy. The first thing that you do, let me first write the general form. So if you are given a number of functions, we have the first function. The first function is equals to f1 with respect to a number of independent variables. A number of independent variables that goes to n, right? And then you're given another function with this and a number of different variables that goes to n. And then these functions, they can be nth number of functions. You can have n number of functions. You have the n number of functions, which is going to be fn is equals to fn, x1, x2, x3, xn. It depends on the book that you're given, but this is the most typical way of representing it. Okay, so now we have a system of equation. This is a system of equation, right? We are given this system of equation. We want to find what you call the Jacobian. It's represented with J. We call it, this is the, we want to find the Jacobian for the system of equation. This is the Jacobian function. We want to find the Jacobian's function, right, for this system of equation. So here we use it. We still use the same principle of partial derivative, but we also apply the principle of determinant of matrices. So first of all, we form this function using the determinant of matrices. So how are we going to do this one? This is how you do it. So you are going to differentiate each of these functions with respect to x1, x2, x3. But how are you then representing this one? So df1, dx1, right? Then you have df1 or df2, with respect to dx1. You have df3 with respect to dx1, right? We have df4 with respect to dx1, which means you can go to dfn with respect to dx1, which means the first row, we are differentiating the functions only with respect to x1, right? With respect to the first variable term there. And then again, you repeat this again. You have now with the second row, you're differentiating df1. Again, now we are differentiating with respect to dx2, and then del f2, del x2, right? And then plus del, it's not plus, I'm so sorry. It's not plus, we are not plusing. We are representing in matrix form. So del f3, del x2, del f4, del x2, and then till del fn, the nth function, you're still differentiating with respect 2. I'm sorry, we're differentiating with respect to 2. So this is going to be del f n del x2. So which means you can go down to del f1. Since this is 1, 2, which means you can go towards to del xn, isn't it? And then go to del f2 over del xn, right? Same thing, del f3, del xn, del f4, del xn, till you get to del fn over del xn. So this is a general way of finding the Jacobian's function. So I think the best way to represent this, how we can apply this, is using let's solve it using a certain problem so that you can see how you apply this. But this is the general formation of the Jacobian's function. So now I'm just going to use an example where we are given that given that u is equals to e minus 2x sine 2y and v is equals to e2x cos 2y, and then you determine the Jacobian for the system of equation. Determine the Jacobian. This is also part of the lecture note. This is one of the typical examples that was on the lecture note. So system of equations. Okay, so how do you go about this one? That's the first question. How do you go about this one? So with this one, we have to find, so we are given u, we are given v, right? Given u, we are given v. So let's find du dx, and du dx is going to be what? For this one, du dx, which means y is a constant, so we are going to have minus 2x, we are going to have minus 2e minus 2x, right, sine 2y, and then let's find del v del x for this one, which is going to be what? Which is going to be 2x cos 2y, right? And then let's also differentiate u with respect to y, right? Let's differentiate u with respect to y. We are going to have del u del y, which is equals to del u del y is going to be 2e minus 2x cos 2y, and then differentiate v with respect to y is going to be what? V with respect to y is going to be, when you're differentiating cos, it's minus 2e 2x sine 2y. So now we have differentiated the functions that were given, u and x, with respect to x and also with respect to y. So this is where we are, right? But now we want to find the system of equations for this one. You want to find the system of equations for this one. So how do we then go about doing this one? So our Jacobian, J is supposed to be, our J is going to be it's going to be dx and dv dx, right? And we're going to have du dy dv dy. So this is remember when you're looking at this function, it was x1 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 x1, but the function was, we're differentiating with respect to x1 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 x1, which means here we are differentiating with respect to only variable which is xx, and then the second one, the second row, it was x2 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 x2. Obviously x1 is not equals to x2, and in our case here we have x is not equals to y, right? So we are going to differentiate with the other variable, which is y, and the functions are changing. This is u, this is v. Here we had f1 f2, right? So they are changing. So this is how you represent it, and at this point we just substitute du dx dv dx du dy dv dy with what we have found here. So this is j is going to be equals to what? What is du dx? Du dx is this. Du dx is minus 2e minus 2x sine 2y, and then dv dx is what? It's 2e 2x cos 2y, and then du dy is 2e minus 2x cos 2y, and then dv du is going to be minus 2e 2x sine 2y. So now, how do you then solve this? For those who have a knowledge on matrices, how to find the determinant of a matrix, this is going to be easy. But for those without the knowledge, this is how you go about solving this one. And I think if you have done statics again, this is something that you should know by now. So if you are given A is equals to AB CD, ABCD, and you want to find the determinant, we want to find A modulus A. So how do you do this one? This is going to be this multiplied by this minus this multiplied by this. So it's going to be AD minus CB. So that's what you're going to do here. So this is my A, B, C, D. So the Jacobian here is going to be equals to, AD, right? Which is this multiplied by this. So we are going to have, if we multiply these two, we are going to have 4, right? We're going to have 4, and if you 4 multiply by, if you're looking at the exponential, when you're multiplying with the same base, we add the powers. If you add the powers, it's going to be 0. So this is going to be sine squared 2y, because we're going to multiply this, then minus CB when you're multiplying C and B. Obviously 2 times 2 is what? It's 4. And then we are multiplying the exponentials, which means we're going to add the powers. It's going to be 0, and then e to the power 0 is 1. and then you multiply the trigonometric functions, which are going to get cos squared 2y. So this your Jacobian here is going to be 4 sine squared 2y minus cos squared 2y. So this is our final conclusion for this one. So this is one of the concepts that we are looking at, and it's very important, especially in applications of partial derivatives. This is one of the crucial concepts that we come about. So yeah, this is where we are going to end. So